This video is going to take us through a walkthrough of two additional calculus FRQs. These are calculator permitted FRQs, and I'll cover two of them in the walkthrough relatively quickly. So if you want to have your calculator, feel free to pause the video and try the questions on your own, and time yourself about 15 minutes per FRQ. Here's the first one. It's a numerical based FRQ. A florist is adding water to a crystal vase, and we have the depth of water in the vase modeled here by a differentiable and increasing function w of t, and the selected values of w are here in the table. So to start off here, it says to approximate w prime of 5. So I'm going to use a symmetric difference quotient. How about w of 6 minus w of 4? And I'll divide that by 6 minus 4. So that would become 1.25 will be the value. You can check that on the calculator. And it says to use proper units. So it says w is in inches, so this is a difference quotient, meaning that 1.25 is inches per second. So it's a rate. It says to use appropriate units, so there's probably a point in that question allotted for the units. Letter B. Approximate the value of the integral from 0 to 9 of w with a left Riemann sum. So if I go back to the table here, I can construct 1, 2, 3, and there's 4 total rectangles. And if I want a left Riemann sum, then I'm going to use the left function output, or for the left corners of each one of those rectangles. Notice that the width, or the delta t, or the delta x length of the rectangle, that width, it varies. So here it's 1. The next width is a 3. The third rectangle has a width of 2, and the final rectangle has a width of 3. So we're going to write down first one, 1 times 1.5 plus 3 times its left corner of 2 plus 2 times the left corner of 5.5 plus 3, delta t of 3 times its left corner of 8. For the Riemann sum, that's going to be 42.5. So there's the approximation of the exact value of the integral. And then it says, is the approximation greater or less than the actual integral itself? Give a reason. Notice back here in the stem, it said that the function w is a strictly increasing function. And if the function is increasing across its domain, then a left Riemann sum, if I go up by left corners, will always be below the actual function curve. So I'm going to have an underestimation of area. So the approximation is less, comma, because anytime it says give a reason for your answer or justify, I'm going to put a comma and then the word because. Because w is strictly increasing. So I have an underestimation from that Riemann sum. Letter C. Here's a second florist filling up a glass vase, and it says the height of this water is given by h of t. This is a function that's provided, so no table, no graph, but I have the height of the water here in inches. So it says to find the average height of the water in this glass vase from 0 to 9. The average value formula is the integral divided by the interval, so divide by 9 minus 0, or I'll put the 1/9 out in front of the integral there. So I'll use math 9 on my calculator to compute this, and I get 4.77936 for that average height, and this is for the glass vase. Is this value greater or less than the approximate average depth of water in the crystal vase? The crystal vase was given to me back here in part A. And so if I want the average value, or the average height here, then I want 1/9 of the integral from 0 to 9 of w. Well, I have the 42.5 as my approximation for the integral from 0 to 9 of w. So take that 42.5 and just divide that by 9. So for the crystal, average depth would be 1/9 of the 42.5. I got that from the Riemann sum from w, and that's going to be 4.722 inches and inches. So it says which one is greater. So the average height of the water is greater in the glass vase. And then letter D, last question here for this FRQ. It says using the model from part C, that's our function, h of t, find h prime of 4. So I'm going to use math 8 on the calculator for this, d dx. If you put in h of t, you can type that in y1. You can type it right there on the home screen, but we want to evaluate that at time 4. So when x equals 4. We're going to have 1.122, and the units will be inches per second. Interpret the meaning of this value in context of the problem. So that means we want to write a sentence. At time 4, what is changing here? Well, the height of water, and specify which vase we're talking about since we have two different functions. This is going to be h of t, which is the glass vase, the height of water in the glass vase. And then the derivative is positive, so is increasing. The height is increasing by the rate of 1.122 inches per second at time 4 seconds. The point distribution would be 2 points for part D. Working backwards, we have 3 points here in part C. Back to part B. B was 3 points for that Riemann sum approximation, and just 1 point for part A. Every FRQ is worth 9 points. Second question in this video here talks about particle motion. So I have a particle P, and its velocity is given here by the function v. Its acceleration is given by the function a. And notice I have an initial condition that the particle P is at position 3 at time 0. So we'll call x the position function, so x of 0 would be time 3. I'm sorry, would be position of 3. When is velocity going to be decreasing? Well, that's going to happen, let's see here, whenever acceleration is negative. So if you graph this, you'll see that that happens on the interval from 0 to 3.067 because my acceleration function, which is right over here, is negative. It says to give a reason, so comma because acceleration is negative on that interval. You'll use your calculator to find the 0 and look for where that x-intercept takes place. Letter B, part B, find the position of the particle P at time 1. So the position function at given time 1, that's going to be x of 1. And what we want to do here now is take a known position, take a given position, which in this case is x of 0. Add to that how the particle moved from 0 to 1, and that in calculus notation is simply the integral of velocity. So here's my starting position where it started, plus how it moved, in this case from 0 to 1. It's a calculator question, so I'm going to use my calculator here. X of 0 is 3, and I'll use math 9 to compute this integral 0 to 1 of velocity. And you can find that on the calculator. Solution should be 4.778. There's the position at time 1. Now, second particle, Q, moves along the x-axis. Its position is given by, there's no function here, x of 1 equals 2 and x of 4 equals 11. Explain why there must be a time when the velocity of particle Q is at 3. Now, velocity is a derivative value of position, so I'm going to think about using the mean value theorem. MVT is the theorem that I use to prove the existence of a derivative value. So let's take a look here. From 1 to 4, well, the change in position divided by change in time is going to give me the velocity. So let's find x of 4 minus x of 1, and we'll divide that by 4 minus 1 for particle Q. So 11 minus 2 divided by 3 is going to give me 9 over 3, which is simply 3. And that difference quotient is exactly the element in question here that I wanted to verify. So let's establish, first of all, continuity, differentiability and continuity, which we need to make sure we have before I use MBT. And it says here that the function x, position function for q is differentiable. So I'm going to say, since x of t for q is differentiable and therefore continuous, by MVT, make sure we state the name of the theorem, there exists a time on the interval from 1 to 4 when the derivative x prime of t, which is velocity of t, is equal to 3. And that's for particle q. So there's a mean value theorem proof embedded in this question. And then lastly, letter D says at time 1, the velocity of particle q, so v of 1, is -3. Are the particles moving toward or away from each other at this time? And then explain your reasoning. Well, let's examine particle p. I need to look at both position and velocity to determine where the particle is and how it's moving. We'll do that also for particle q. So at time 1, we found that to be 4.778 for particle p, and the velocity at time 1 of particle p is 1.336. Particle q, so its position at time 1, that was given up there as 2. Its velocity at time 1 is given right here as -3. So what this means is particle p is, here's my number line, particle p is at 4.778. Particle q is at 2. So there's particle q. But notice the velocity of q is negative, so it's moving left. The velocity of p is positive, so it's moving right. The particles are moving away from each other. And you could express that by saying q is moving left from its point of x equals 2, and p is moving right from its point of x equals 4.778. Something like that would be considered a good enough reasoning and explanation for what's happening with those two particles. That's a 2-point part right there, +2. Letter C is also 2 points. Backtracking to part B, find the position. This is a 3-pointer. And then for part A, a 2-pointer. And there's your total of 9 points. So that's an example of a particle motion problem. Again, both of these FRQs were calculator active. So review the calculator keystrokes using the TI is Math 9 for definite integral values, and then Math 8 to find derivative values at a given point. Thank you so much for watching. I hope that was helpful for you, and good luck with all of your future FRQs.